So today, now we've seen some of the applications of speed and velocity formulas. We are actually going to reformulate them, or rewrite them in ways that are really, really useful to us in solving a lot of different problems, describing the motion of things. But we're going to start with just our originals. So we've got acceleration is the change in velocity over time, which we will often expand as v final minus v initial over t. We've seen that one before. And then we will do velocity, which is an average velocity. Same as we've been using, and that's a change in position over time, like so. And we're going to make a couple assumptions for this, just to make it easy on ourselves. Things that we can really do pretty much every time we run a problem. Namely, that our initial position is at 0 meters. And it doesn't really matter where we are, we're just going to call that position 0. We can basically say one place is 0 every time we do a problem. And what that means is that this delta x, which is x final minus x initial over t, that x initial is 0. We can really just write that as the velocity is x over t. Just how far did it go over time. And that's really just a way to help change our place. So we can do that. And then the other thing is that we will start our timer at t equals 0 meters, 0 seconds. And so that's why I don't have, technically these would be delta t's as well, but if we're always starting at 0, we're just going to use t. So those are just shorthand corrections that we make just to keep from writing delta all the time. We will still see it some. So let's look at this equation. We're going to rewrite this in a little different form. It means the same thing. But if we've got that acceleration is equal to final velocity minus initial velocity over t, we can multiply both sides by t and get that the final velocity minus the initial velocity is equal to the acceleration times time. Or that the final velocity is equal to the initial velocity plus the acceleration times time. This is really just a rewriting of the first way because we so often want to learn what the final velocity of an object is. We know how fast it's going now. If it undergoes some acceleration for a certain amount of time, what new velocity will it have? So that'll be our first big one. Now the second one goes to our velocity. And when we defined velocity up here as the change in x position over time, which sometimes can just be written x, we're actually describing the average velocity there. Because it could vary a little bit during this time. All we're measuring is how far did it go and how long did it take. But for parts of that, it could be going faster. It could even be going backwards for some, or in the opposite direction. And if this is the average velocity, there's another way we can find average velocity, and that is to take, there's your fraction, Hannah, 1/2 of the sum of the two velocities, so v initial plus v final. That's just another definition of what average is. I'm going to go ahead and solve this for my delta x now, and we're going to make one substitution right off the bat, or as we go. We're going to rewrite the final velocity in here from what we already found up above. So, to take our next step, I'm going to multiply through both sides by t, so that leaves just delta x over here. It gives me t over 2 times the quantity of now whatever is left in here, v initial from here, and now my substituted value of v final, which is v initial plus the acceleration times time. And now I'm going to simplify this stuff in the next couple of steps to get it into a handier formula. So we have t over 2 times our first one, which is 2 times vi. And then we have the t over 2 times the second term, a times t, and one last step, delta x is equal to, the 2's cancel, of course, the initial velocity times t, plus, I'm just going to take the 1/2 out, a out, but we have a t times a t, that becomes t squared. So this one's really useful if we want to figure out how far is something going to go. We need to know how fast it was going at the beginning, how long it was moving, and if there was any acceleration in that. But if we know that, we can quickly say how far has it gone. We're going to practice all of these right afterwards. So right now it's just showing you where they're coming from.
How did the t get on top of the t?
I multiplied both sides up here by t, so that canceled the t on this side, but got a t on the top over here. And please do stop me, because we'll go through these occasionally where I'm not expecting you to remember how to derive these. I just want you to see where they come from, because they're not magic. These are actually often credited to Galileo, who did the first work understanding acceleration as he rolled wooden balls down a ramp and measured how do their velocities change, how long does it take to go from the top to the bottom depending on their angle and whatnot. And if memory serves, he was doing that measurement with hourglasses. So think about that next time you pull out a stopwatch or use photo gates or whatnot. He actually, little known fact, Galileo did not have photo gates to use in his experiments. Did you have a question, Bobby, or did I answer it?
You answered it.
Yeah. So the fact that you don't need to memorize how to do this. No, we are going to use the equations a lot, but the equations will also appear on the test. So I always try and have room to put the equations up there. Our next one is going back a couple steps. We're going to use that definition of average velocity, which was 1/2 times the sum of the two. I don't even memorize them. I always go off my cheat sheet. I did it once upon a time, but I don't need them all. And that was equal to the change in x over t, but I'm going to, for the purposes of this, multiply it through by t right away. And so on my left side, I'm just going to start with the delta x. But this is basically our two definitions of average velocity, and we used it more or less up here. And we are also going to say, do the expansion that if acceleration is v final minus v initial over t, if I want to solve this for t, I multiply both sides by t, so I have t like so. And then I'd also divide by a. So that would leave me with the a's canceling here, just a t on that side, which would be a v final minus v initial over acceleration. And if you guessed that we were going to substitute that up here, then you guessed correctly. So we're just going to substitute it in there and then evaluate what we have. So we'd have delta x, of course, still on the left side. We'd have 1/2 times this quantity, vi plus vf. But now we're going to put that in. So we'd have vf minus vi over a. Now we're going to just do our distributive thing in there. We have 1/2. This will all be over, I'm just going to put it all over 2a, so I'm combining the 1/2 here and the a on the bottom. And we'll get rid of that in a sec. What do I get from this part? Well, the middle terms cancel out, right? Because we have positive and negative. Maybe I should just go through. So we have vi times vf from these two. negative VI squared there. VF times VF is VF squared. And then VF times negative VI is a negative VI VF. I'll move this down in just a sec. See how much I can move down. Oh, your brain is just stretching, that's why it hurts. And notice I've got a positive term here, VI, VF, and a negative term, so those actually cancel. So that becomes delta x over is equal to negative VI squared plus VF squared over 2a, and this one's usually solved for neatness, I guess, for the VF squared. So that means I have to multiply both sides by the 2a equals negative VI squared plus VF squared. And now I'm going to solve for this one, so I'll add this to both terms, but I'm also going to flip it around just so I have VF squared equals. So that's what's left here. I add this to both sides, the initial squared plus 2a delta x. And that is our third and final important one. So I'm going to rewrite the other two down here as well for reference. These three help us describe any of the motions that we're doing. And really, they're just rewritings of what our definition of acceleration and what our definition of velocity are, but these forms help us quite a bit, because we can also say V initial, or V final is equal to V initial plus AT, or our change in position is equal to V initial T plus 1/2 AT squared. So these three we refer to sometimes as the Galilean equations. I don't know if he actually developed them or wrote them in this way, but since they're based on the concepts that he developed, we named them after him. And these three will help us with a lot of our calculations.
So the second one that's not boxed,
Yep.
what does that describe again?
Well, let's see what each of these means. What does VF mean? V final. So at the end of a time window, here's the velocity. What about that? Initial. So what's its speed or velocity at the beginning? Acceleration and time. So what this is saying is, if we want to know how fast something is going in the future, if we know how fast it started, what its acceleration was, and for how long, we can figure that out. So let's just take a quick example. Let's say that something is going 10 meters per second, and it's accelerating at 2 meters per second. So every second it's going 2 meters per second faster. And let's say that we want it in 5 seconds. So if it started at 10 meters per second, and then every second it's going 2 meters per second faster, after 5 seconds that would be 10 meters per second faster. We'd now be going 20 meters per second. So the final speed would be 10 plus 10, or 20 meters per second. That's what VF would be. Yep. Well, let's take a couple other examples here. Oops. So I'm going to pause our video while I write out a few other ones. Make sure you've got these three formulas handy. So a good question, why would I ever use this one? When we have a problem, we don't necessarily have every single bit of information. If we did, there would be no calculation at all. So this one's really useful if we know the initial velocity, the acceleration, and time. What if we don't know how long it was going? What if instead we said, well, I know how fast it's accelerating and I can measure how far it's gone. So say I can measure how far it's fallen off of a cliff, but using a stopwatch for time is really, really hard. It's almost impossible. So instead, I know how far something's fallen and how fast it's been accelerating. I want to find out how fast it's going. This one allows me to not know the time. If instead I know the distance it's moved, I can still figure out how fast it's going. Down here, I might want to know if I drop this cliff or this rock off a cliff, and someone is standing down below, how long do I have to gloat before it gets bloody? Real world situation. Well, if I know how high the cliff is, I can figure out how long it will take. Likewise, if I want to say, okay, this bomb's going to explode in 5 seconds. Quick. Will we be far enough away? Really, you're just going to push it out of the plane or whatever and hope for the best. But while your friend's doing that, you might sit down and say, how far away is that bomb going to be if I push it off the cliff and I know that I've got 5 seconds?
I feel like they would have enough time to think
Yes,
about
just
that.
give me a moment. There's no time.
Measuring distance.
So this one measures the distance that something would move in that time. Uh-huh.
What were the 3 equations that were boxed?
These 3.
Those 3?
Yep.
Distance. And super amount of time.
We're going to practice these. Kind of keep in mind, we're only using, 5 terms. The delta x, this could be in any dimension, but it means how far does it go in a straight line. The initial velocity, the final velocity, the acceleration, and the time. And through combining these in different ways, it makes it easier to solve certain types of problems. Okay, let's run through how to solve some of these problems. Certainly, it's not something that you might do every single day, but now that you will be able to do them, you might find that you do them occasionally, just for fun. So Sean's got a van, and it can accelerate at 2.2 meters per second. First question is, how long does it take to get to 25 meters per second from a stop? So let's write down stuff that we know already. What are we trying to find in this question? Time. What else do we know? We know acceleration, that was given in the first part, 2.2 meters per second.
Would VI be 0?
Why?
Since you're at it's from a stop.
It's from a stop, so VI would be 0. And V final, so we know that these are initial and final because of when they come during the question and the wording around them. If he is at a stop, so he's from a stop, that means it happened first. And it gets to 25 meters per second, that means it happened second. Now we go over here and say which of these equations are going to help us find, we know we need a time in it. So first off, which of them have time? Well, only these 2 have time. Which of them have all the rest of the information in? Well, this one we know V final, we know V initial, and we know acceleration, so that's a good candidate. Down here, we don't know how far he went.
25 meters per second.
No, that's how fast.
So fast.
It doesn't tell us how far he went. We're saving that for later. We know its initial time, well, oh boy, it's got 2 terms. If we want time from that one, we have to solve a quadratic equation. So sometimes we will want time, and what we're given is enough to do this. There are always 2 ways to solve these problems, and we'll see examples. One way would be to solve a quadratic equation. Another would be to take it 2 steps. Solve a different equation first for whatever we're lacking here, and then solve it.
When we're solving problems, can we only use those equations, or can we use other?
You can, well, if you want to, I don't know which other ones you want, but don't forget that average velocity is the change in position over time, and average acceleration is the change in velocity over time. Those are also useful and can be even easier rather than starting here and rearranging, but these are all essentially the same.
All right.
I don't know if there are other ones, but we could talk about that offline.
That was just one that you just showed that we could drop off the board.
Gotcha. Oh, you can certainly use that.
All right.
Its usefulness might be limited. Okay, so let's put, we are going to use our first one, we're going to rearrange that and solve for the time. So we have to subtract VI from both sides, and then we're going to have to divide by A. So you guys do that while I answer my phone. Okay, so when we do that, we subtract initial velocity and then we divide by the acceleration. So we have VF minus VI over acceleration here, and then we've taken care of everything else here, so that's just time. We can put our values in. So V final is 25 meters per second minus 0 over the acceleration of 2.2 meters per second. We get 11 point something now? 11.36, but 2 sig figs. So I'm going to put that here with a little mark that we only have the 2 sig figs. What are our units? Seconds. The meters per second cancel with the meters per second, leaving time to go up above. So 11 seconds. Good.
Interesting.
That is a slow, man.
It's not that good though.
It's not that good? More than 11. Next question, how far does he travel during that time? So a couple of good points and questions in here. Certainly since we're trying to find a how far, these two questions have a how far. And actually either of them would work. So we might just solve it with both ways. But we did just find the time, so we can solve it this way. The time we'll use all of the digits here and then round later. That's why I wrote the extra ones up. But sig figs we usually just find at the end. So if we quickly do our second equation there, delta x is equal to our initial velocity of 0 meters per second times some time, which I don't even care about, plus 1/2 times his acceleration of 2.2 meters per second, times the square of this time. That's a very commonly missed or squared. The square is very commonly missed, is what I'm trying to say. So we don't care about the first term since we started out at 0. So we get 0.5 times 2.2 times 11.36 squared, or 142 meters.
Well, wouldn't it be 140 since we only have 2 sig figs?
You are right. Yep. Yep. 140. Thank you.
You want to stay and do the third one?
Yeah. Let's do this last one together. I want to quickly, if I rearrange our third formula over there, I subtract the VI squared from both sides, and then I divide the 2a. So I get that delta x is equal to VF squared minus VI squared, and then divide the 2a. That would work out to VF was 25 meters per second squared over 2 times his acceleration of 2.2 meters per second squared, or meters per second. 20, that's 625 divided by 2 divided by 2.2. Oh my gosh, it's 142 meters again. So 140 meters with 2 sig figs. What's that? I solved this equation for the delta x. So I subtracted out v initial, which is 0. Then divided both sides by 2a. So that's where we got this part. I just want to go through them quickly. And if you miss a step that we're doing, check out the video, which I'll upload 4th hour. Last one, how fast could he get it going in the first 100 meters of a race? That's a good one for here too. We don't know the time for that 100 meters, so we can't figure that out. Our last equation, we want a V final. So no, the initial or final velocity we don't know. We want to find out how fast would he be going after a certain amount of time. The V initial squared, that V initial is still 0, right, from a stop. So you'll see this sort of thing. Plus 2 times his acceleration here, 2.2 meters per second squared, times how far he traveled, the delta x, which here is 100 meters. So V final squared is 440, and it's going to be meters times meters, so meters squared per second squared. And then what is the square root of that?
Square root of 440.
I think so. 20.97, so 21. What are our units? Meter, no. Take the square root of that, so meters per second. So you'd be going 21 meters per second after 100 meters. Our book problems, let's see.